Hello, my name is Jorge Acuña, and in this presentation, we are going to go over an introduction of fractional dimension RTA. In case you want to learn more, you can visit us at our website, jacunaconsulting.com. This is what we will cover in this presentation. First, a brief introduction. Then we will answer the question, do we really need a new RTA method? Then I will explain how it works. I will talk about fractals and fracture swarm models. Then I will show how we obtain the typical unconventional well responses with fracture swarm models, and then discuss differences between the classic RTA and the fractional dimension RTA. I will explain both in the next slide, and finally, some conclusions. As most of us are already aware, there has been a great effort in the industry to explore the geometry of the fractures inside the SRB of unconventional wells. These two publications here are very good references, and I recommend you to read them. Many interesting facts with respect to the unconventional well fracture geometry. For example, they found that the hydraulic fractures are numerous and broadly parallel with many more fractures than perforation clusters. They form swarms, that means groups of fractures with very short spacing. And the fractures show deflection, offset, and branching and heterogeneities, and that creates very complex geometry. Also, they did something interesting. They took plugs next to the hydraulic fractures and they measured permeability. And what they found is that the permeability was pretty much the same, close to the fractures of a well. So what that means is that they found no evidence of enhanced permeability regions next to the hydraulic fractures. With all those facts in mind, so let's look at what is the classic RTA versus the fractional dimension RTA. The classic RTA was developed for equally spaced fractures. And as we all know, we get the parameter A square root of K. The fractional dimension RTA was developed for complex systems of fractures. What do we mean? We mean fracture systems that could be equally spaced, but they could be unequally spaced in what we call fracture swarm models, or they could even be complex like this, for example. Instead of obtaining this parameter A square root of K, we obtain the parameter A K to the power delta. When this parameter delta happens to be equal to 0.5, we revert to the equally spaced fractures. This method, I developed this method while working at Chevron between the year 2016 and 2020. But the method has been already published and it is available in commercial software. So let's try to answer the question, do we really need a new RTA method? Let's consider these two wells. These are models, really. So we will work with simulated example just because we know the answer. So these two wells have the same number of fractures, same fracture half length, same fluid properties, permeability, porosity, etc. Same volume. The only difference is the fracture spacing. Now, when we impose the same pressure history to both wells, this is the response that we get. The upper curve is cumulative production. The lower curve is flow rate. The blue corresponds to the equally spaced model. The red corresponds to the unequally spaced model. You immediately see a dramatic difference between the two responses. So what we find from this example is that the fracture spacing is a parameter that determines the performance of the well, much more than we would like to believe. Now let's say that I take this production data, my flow rates and my pressures, and I analyze them. So I will take the results from the equally spaced model. And these are the correct parameters. I know them because this is a simulated example. And here are the properties that I use. So I took the simulated data, applied the classic RTA method, and these are the results that I get, which are correct. I'm able to match this log-log diagnostic plot, that is the plot to use instead of the square root of time plot. And then I am able to match history very, very well. If I analyze the same data with the fractional dimension RTA of FD-RTA, I obtain the exact same results. Well, not exactly the same, but I obtain correct results. for cases in which the fractures are equally spaced. So as long as the fractures are equally spaced, the classic RTA works just fine. But let's apply it to the unequally spaced model. And again, I know the answer. So I apply my pressures and flow rates and I analyze them and I obtain the best possible fit, and this is what I get. I obtain that my fracture half length is 69,000, even though the actual value is 149,000. Fracture area is proportional to this. SRB volume is much smaller than the actual one. And the results are obviously off. Now somebody might say, well, your history match is not as good, etc. But the thing is that we are trying to fit this diagnostic plot with this shape, and it is almost impossible. I let the software select the best fitting response, and this is what we get. Now, if I use FD-RTA, I'm able to get the correct response. And notice the difference in the match for the diagnostic plot and for the history match. So you see, because we never know what type of fracture network we have, if we believe that the classic RTA is giving us the correct response, then we are assuming that we have equally spaced fractures. And based on the evidence that we have, that is not the case. In the majority of the cases. In that case, you might end up with an underestimation of frac length and fracture area and SRB volume. Now let's see how the FD-RTA works. When we have equally spaced fractures, the way we solve these problems is by just selecting what we call a symmetry element. We select a part of the network and we solve the flow equations there. And because of symmetry, we are able to apply the results this and multiply by the number of pieces that we have that look exactly the same as this one. So 1, 2, 3, 4, etc. And we multiply the results of a single piece times the number of fractures. But when we have a fracture swarm model, that doesn't work because there is no such thing as a symmetry element here. Some of them are bigger than the other one. And of course, if we have a random network of fractures like this, that this is just I created a random network. That's what I did here. But in general, this illustrates the complex geometry that we might find in the wells. Of course, there is nothing even close to a symmetry element here. So how do we do to solve this problem? For that, I invented this technique. For example, for butterfly models, I call them butterfly models. For this to work, the conductivity of the fractures has to be large. And what that means is that the actual conductivity divided by the matrix perm times XF, that is the half length of a single fracture, has to be greater than 300. Because our K, the matrix perm, is so low in conventional wells, this is very easy to achieve. In fact, with a fracture conductivity of something like 10 millidarcy feet, and a permeability of 100 nanodarcy, I already achieved this limit. And if the matrix perm is 10 nanodarcy, then this would be 1 millidarcy feet. We could discuss what that means. But in any case, what we do is the following. We take this part of the system and the other half, and we put them here side by side with the fracture in the middle. And then we take the next one and put it here, and the next one and put it here. So what I do is I align the fractures in a single very long fracture that will represent the SRB area. Like this. And again, the reason I could do that is because the conductivity of the fractures is large. So I can assume that the pressure in the fracture, this is the well, by the way, the pressure in the fractures is the same. So as long as that is the case, I can reaccommodate these fragments in this way. Notice that here in the middle of a fracture there is a hydraulic no-flow boundary, because when the flow is fully developed, there is no fluid going across that boundary. It either flows to this fracture or to the other one, usually to the closest fracture. So because of the existence of that hydraulic no-flow boundary, I'm able to cut the system like this. Now, how about the area outside of the SRB? I just come up with an analytical way of estimating how this changes with distance from the fractures, and I just put it here as the wings of a butterfly. That's where the name comes from. This is the actual shape of a butterfly model for a system like this, Now, the nice thing is that the performance of this system and this is the same, as I will show later. But let's apply it to this system that is our fracture swarm model. In this case, I take one half and then a narrower half, and then I organize them like this with the thicker ones at the center, and then the medium ones at the middle and the thinner ones at the extreme. So I end up with this, and then the area outside of the SRB, I put it here as additional area. So my entire frac length is here. And of course, the y-axis is scaled down just to fit the page. And this is how the actual butterfly model looks like. Remember, the performance of this and this is the same, and that is why this works. This is how the butterfly models are constructed and how they work. But how do I do when the fracture network is really complex like this? Well, in this case, the method is a little more cumbersome. What I showed before doesn't quite work for this. What I do is I contour my reservoir volume with distance from the fracture. Each one of these contours is drawn at the same distance from the fractures. When I say the fractures, that means the closest fracture. So what that means is that, you know, this line that goes here is at the same distance from the fracture network, that is this entire object, the black lines together. And if I measure the area inside each one of the contours versus the distance of the contours, I obtain this plot that is called the characteristic flow volume curve, or CFV. This is a plot of reservoir volume versus distance from the fractures. Once I have this plot, what I do is I approximate this with the straight lines in log-log, and these straight lines become power laws, and the slope of them is 2 delta. Here, for example, I have 3 segments, one of them from 0 to 30, the other one from 30 to 330, and the other one from 330 on. You see, with this, I'm able to create a system with 3 segments that I can convert into a butterfly model. This first segment from the fracture up to here, that would be from 0 to 30. The next one from here to here will be from 30 to 330, and the third segment is from here to here. Notice that the area is not continuous in the interface, but the volume is. So the area perpendicular to flow is not continuous, but the volume is. You know, that's how it works. Now let's do simulation in both systems here. In black we have the random network, and in red we have the butterfly model. So as we saw, the CFV, or characteristic flow volume, is pretty much the same. And using the theory that I have in the papers that I have published, you could convert that distance into time, and that is shown here. So this is volume versus time. If I were to produce both systems at constant flow, this is the pressure transient response. That would be the pressure, or normalized pressure, delta P divided by Q, and this would be the pressure derivative. And then you see that the performance of the random network and the butterfly model is pretty much the same. This is for single phase, of course. Now for multi-phase, we will discuss that in a little bit. The RTA response is the response to constant pressure. In that case, I don't plot the pressure because it's constant. I plot my cumulative production normalized to pressure, that is here, the upper curve, and my flow rate, that is here, lowercase q. This one is just the log derivative of cumulative production. But you see, the performance is the same. Now, pay attention to this part because it's the most important thing. The shape of the normalized cumulative production to pressure and the CFB is the same. What that means is that I don't need to know this geometry to obtain the performance. What I do is analyze the performance and obtain the CFB. And then with the CFB curve, that is the variation of volume versus distance or versus time, I'm able to create a model. So I could go backwards from flow data, that is flow rate or cumulative production and pressure. I can get back to a model that will reproduce that exact behavior. And I don't need to go through the original geometry that created the response. And that is how this CFB works. Now let's back up a little bit, and this part should have been presented at the very beginning of the talk. But the thing is that we needed some concepts to actually understand what it is. Let's see, when we see the response of a typical well, typical and conventional well, this is what we see. We see a slope there, but we were expecting to see what we call linear flow. That means equally spaced fractures flow. If that was the case, this slope should be 0.5, but actually it's not. It's steeper than 0.5. We know that the boundary dominated flow has a slope of 1. That would be here. That's it. This is the pressure derivative in the log-log plot. So you see that what we get is a response that is in between. It's not the response of equally spaced fracture system, and it is not the response of boundary dominated flow. So it's something in between. For a typical gas wells, what we get is a first part that is much flatter than 0.5, but it's not horizontal. It's not like radial flow, what we would expect for a vertical well in a homogeneous system. But it is not linear either, so it is something in between. So the unconventional wells show flow regimes that are not the typical ones. They are not boundary dominated flow, they are not linear, they are not radial, but they are something that we will call it in between. Now, let me introduce the concept of fractals. These are fractal network of fractures. I studied this for my dissertation at USC in the early 90s. And the important thing, these fractal objects, the fractals are these three that you see here. They are what they are called scale invariant. They look the same at different scales. What that means is if I take a piece of the entire object, it looks like the entire object. And that is a characteristic of fractal networks. Now, in simpler words, the fracture networks of fractures are made up of rock pieces of different size. So, you have many more fragments of a smaller size than larger sizes. But in general, what you see is that the pieces have different size. And they have fractal or fractional, that means non-integer dimension. For example, here, these are the two extreme cases for this one that have this one has a dimension of 2. What that means is that they fill the embedding dimension. The embedding dimension is the one in which the network exists. In this case, is the two-dimensional space. What that means is that if we go to the third dimension, we don't see anything fractal. We just see, something like parallel lines. If we were to see this from this side, let's say this has some thickness, but we don't see it because we are looking at it from the top. Anyway, the reason I mentioned the embedding dimension is because we have a three-dimensional fractal networks like this one, where the embedding dimension is 3. They exist in the three-dimensional space. But this one, they exist in the two-dimensional space. So between the dimension of 2 and dimension of 1, I have these networks that fill the gap and give you dimensions that are not integer. They are fractional. But the most important feature of these networks is that the hydraulic behavior of these ones, it is in between the behavior of a single fracture and the behavior of radial flow. That would be if I imagine I have a vertical well here, the network of fractures is so dense that this will behave like a radial flow in a homogeneous system. Actually, these ones give you behavior in between, and that is the idea that I took advantage of to analyze unconventional wells. Of course, an unconventional well doesn't look like anything like this. The unconventional well looks more like this. But what I did is I create a fractal in 1D. What that means is that the fractal is given by the gaps of fractures along the well length. For example, here, if I put my fractures very close together, that my entire frac length is full of fractures, and I analyze the flow of this system, what I will see is it will transition to boundary dominated flow very quickly, and this is what I see here, a slope of 1. If I start to create gaps, now notice that the graph changes, the slope becomes flatter, and the pressure derivative start to separate. This has a flow dimension of 0.1, flow dimension of 0.2, it's even flatter here. Flow dimension of 0.3, even flatter, 0.4, 0.5, this is linear flow with the slope of 0.5. So this is how I create behaviors in between boundary dominated flow and linear flow here. And the slope is always 1 minus delta. So when I analyze a well and I obtain a particular shape in the derivative, I am able to construct a model that will give me exactly that response. And that is the power of this approach. Now let's see how this works with reservoir simulation. Let's remember the two typical responses. I am able to explain this one with the slopes between 0.5 and 1, but I am not able to explain this one yet. And this one is called subradial flow. This one is called sublinear flow. When the slope is steeper than 0.5, less than 1, is called sublinear. When the slope is flatter than 0.5, but more than 0, we call it subradial. Here is one of those fracture swarm models constructed with these parameters. And I simulate, I impose this pressure, I calculate flow rate here, cumulative production here, I analyze, and this is the diagnostic plot that I get. As you see, I see a single slope here that is 0.71, that is 1 minus delta. What creates this single slope is that when I start to flow, the entire frac length, because the conductivity is large, it propagates immediately to the tips of the fractures, and then it starts to advance perpendicular to the fractures. While this is advancing into the matrix, this segment, let's say, this part of the network is behaving as linear flow. The slope would be 0.5, but these ones where the fractures are closely spaced, they already touch the boundary coming from the other fracture. So they behave as boundary dominated flow where the slope is 1. So we have some segments with a slope of 0.5, some segments with a slope of 1, and then the mix between them will behave with a slope that is something in between like this. The more closely spaced fractures I have, the closer this slope becomes to 1. The more regular the spacing is, this starts to being close to 0.5. Now let's reduce the fracture conductivity to 10. I get the exact same response. I will compare them at the end. Now pay attention, because now I'm going to really reduce this to something much smaller, 2.2. Now notice the difference. Initially I have a single slope. Now I have two. One is much flatter than 0.5. This is how I create what we call subradial flow. What that means, what happens during this period is that it takes some time. I'm hitting my well somewhere, it's not shown here. After some time, my drainage area propagates along the fractures and perpendicular to the fractures. During that period, I see this slope that is somewhat similar to bilinear flow that we see in finite conductivity fractures. Eventually, when we reach the tips of the fractures, it can only propagate perpendicular to the fractures, and we revert to this behavior that is the behavior that we had before, that we had here in our system with high conductivity. If I reduce my conductivity even more from 0.2 to, let's say, 0.05, what I do is I make this segment much longer. So let's go into insights into well behavior. Now, very early on, when I start to produce, this is my fracture spacing, by the way. Here is fracture spacing of 2 all the way to fracture spacing of 50. Initially, every single fracture produces the same because they are connected to the same area of matrix. But as time goes on, the ones that are closely spaced, the production starts to decline very quickly. And then the next ones, where the fracture spacing is wider, they start to decline by later in time. Late in the life of the well, only the fracture spacing with a larger fracture spacing, those are the ones that sustain flow. The other ones are already, the production is too low. That is for the individual fragments. Now, when we combine these fragments into systems where you have different amounts of the different fragment sizes, this is what we get. delta 1 means that I have a lot of smaller fragments. What that means is that the initial production is large, but the decline is much faster. When delta approaches 0.5, I only have larger fragments. What that means is that the initial production is smaller, but the decline is less. Now, notice that the initial production is a function of how many fractures you have. The more closer spacings you have, the longer the total frac length you have. That's why when delta is smaller, you produce more initially. But because the drainage area associated to these smaller fractures is much smaller, they start to dry up, and then you get a much larger decline. So that is the effect of delta in the initial production and decline. So lower delta networks produce more initially but decline faster. Now let's look into flow profile along the well. Let's say that initially, you know, I am able to run you know, one of those production logs here and measure how much fluid is coming in at the different positions in the well. What I will find at very early times is that this area produces a lot initially, but they dry up quickly. So if I come back, let's say 6 months, a year later, what I find is that this doesn't produce anymore. But fractures like this that are kind of isolated, they keep producing, because at the end, the fractures associated to larger drainage area are the ones who sustain production. The ones that are closely spaced, they cannot sustain production because they run out of drainage area. So this means that the flow profile along the well changes with time. Now notice that this can be erroneously attributed to fracture closing or fracture closure process. For example, we see that initially this produces a lot, and we come back a few months later and then it doesn't produce anymore. What is the conclusion? Oh, my connection to the wellbore got blocked, we have damage, the fracture is closed. In reality, that is a result of the geometry of the fractures, and that is very important to analyze, to understand. Why is that? Because, for example, you want to do remedial work for this particular well, and you know that this part used to produce a lot, but now it doesn't produce. Somebody might suggest, oh, let's refract this part, you know, and that might not solve the problem. So the importance of this way of thinking about wells and how they behave, and the role of the fracture spacing being variable or not, is that it gives you new insights into well behavior. It might lead you to better decisions in terms of how to enhance recovery, how to understand what is going on. Let me give you another example. For example, here, because this is a multiphase well, and here I am analyzing single fragments. This is the fracture spacing, by the way. So here are the pieces with the small fracture spacing. Here are the ones with large fracture spacing, and this is the GOR. When the fragments start to dry up, the production of oil starts to come down, and then they start to release a lot of gas, or maybe the same amount of gas, but because the oil comes down, the GOR, that is the ratio of gas to oil, it starts to go up. So eventually, for all fragments, it will eventually go up, but the fragments with that are much larger, they take longer for that to occur. But the smaller fragments, you get that they go to very high GOR relatively quickly. So what happens when I combine the different fragment sizes into networks? Well, the networks that have a lot of this, they're gonna give you larger GOR. That would be this one, for example, where my delta is small. Remember that delta is small means that you have a lot of closely spaced fractures. Delta large, 0.5 or so, that means that you only have fractures that, you know, have a regularly spaced at a much larger spacing. In that case, the GOR remains low and eventually it takes off. But you see how this fracture geometry affects the GOR. Because the lower delta network have a larger proportion of smaller fragments, these networks give you larger gas-oil ratio. So what is the FD-RTA workflow? Well, we start with production data, meaning flow rates, pressure, etc. We feed that with a model. The model will give us the XMF, skin, delta. And then with these parameters, we are able to create two types of model. We could create the fracture swarm model like this, or we could create a butterfly model like this. And with any of the two, I am able to simulate, even in multiphase, and I'm showing a multiphase run, but you know, you could do it a single phase if you want to. What is the difference between the two? Well, in terms of results, they are very close. They are not exactly the same because these are numerical approximations too. And you know, there are finite size effects and everything. But if you compare the flow of the different phases and the pressure, the simulated data are the lines and the symbols are the data. What you see is that they are very close, except that the fracture swarm produces maybe less gas later on. The big difference is that the butterfly model, the run time is 5 seconds in multiphase for this run. That is like a year and a half or so. For the fracture swarm model, because you have too many fractures, what I did is I have to reduce the size to 1/10 of the original size, run like that, and then multiply the result by 10. But still, it took 6 hours to complete the same run. So the results are comparable. They run in multiphase, both of them, but this one runs much faster. And this is the power of butterfly models. It allows you to get to multiphase results in a very, very fast compared to creating a model of the actual fracture swarm model. How do we do long-term predictions? Well, that depends on the type of boundary conditions. You need to put boundary conditions to make long-term predictions because, you know, otherwise you are assuming that the well is sitting there unbounded, meaning that there are no wells around it. But if you have a well to the side, you have to put a no-flow boundary here. My active well is in red, and some flowing well that is not being analyzed is here in black. Here, when you have two wells flowing, we talk about the hydraulic flow boundary that is created between two flowing wells, and that represents a no-flow boundary here. It's a hydraulic no-flow boundary. The wells could be communicated, but when they flow together, there is a hydraulic no-flow boundary that forms between them. If the well is in the middle of a path, you need to put two of these no-flow boundaries, one at each side. And if the well is surrounded by wells, we have to put no-flow boundaries at all sides. Normally, the effect of these extra boundaries is small, just because this is very short compared to this dimension. But once you have this in place, then you should be able to do your long-term predictions to, I don't know, 20 years or whatever you want to use. Let's look about the difference between Classic RTA and Fractional Dimension RTA. A Classic RTA is for equally spaced fractures. FD-RTA is for equally spaced and complex network of fractures. Classic RTA, it gives shorter total frac length when your system is actually non-equally spaced systems, while the FD-RTA gives you the actual, that is longer normal, total frac length for non-equally spaced fracture system. Now, because the total frac length is usually short, when you are trying to set up a numerical model, you're going to need, for Classic RTA, enhanced permeability regions. That means areas, matrix areas next to the fractures that have a much larger permeability than the actual matrix perm. In this, because the actual frac length is much longer, you do not require enhanced permeability regions. The SRB size is smaller than well length times 2 times the fracture half length. Here, we assume that it is the same, so it's one less unknown. In Classic RTA, when we are modeling high decline, normally that requires a pressure-dependent permeability. Here, we obtain the high decline with lower delta. In Classic RTA, it's difficult to match the GOR trends, but here the GOR trends are created by fracture complexity and depend on the value of delta. So you see there are a lot of things and insights that you can get by thinking about unconventional wells using these terms and these new concepts of of geometry, with variable fracture spacing, areas of closely spaced fractures versus areas where the fractures are more widely spaced. So let's go to conclusions. So the fractional dimension RTA of FD-RTA is a general method for simple and complex network of fractures. So we can analyze equally spaced fractures, and we will obtain the same result that classic RTA. Now, something important is that the wells with complex network of fractures or with variable fracture spacing perform very differently from wells with equally spaced fractures. And this method was developed to deal with wells with complex fracture geometry, and it has been tested numerically. It works in multiphase wells, including condensate wells. It gives you new parameters to characterize unconventional wells. It gives you this parameter delta, that is a function of how the rock breaks, and it gives you XMF, that is the total frac length, that you can just use these parameters to correlate with the completion parameters, with geologic parameters, etc. Now, the FD-RTA is available in commercial software, and there is online training available at this website. So I invite you to check it out. So, and with this, we reach the end of the presentation. Thank you very much for your attention.